Hello, I'm going to go through the complex numbers paper from your exams. Okay, so question 1. So part A is if U equals 3 cis of pi over 2 and V is equal to 5 cis pi over 6, then find U squared V. So we need to find the products of these two complex numbers, but we should first square U first. So that'll be 9 cis of pi, because using Demoivre's theorem, squaring this, you square the 3, and with the cis you have to multiply it by the power inside there. So then just multiplying these two together, U squared V is going to be 9 cis of pi multiplied by 5 cis of pi over 6. And then the two constants at the front just multiply to each other to give you 45. And then the arguments of the cis inside there, you just add them together. So it'll be cis of pi plus pi over 6, which simplifies to 45 cis of 7 pi over 6. Okay, on to part B. Write that cubic over x minus 4 in the form of a quadratic plus a remainder over the linear factor. So here we're going to divide this cubic, x cubed minus 5x squared minus 6x plus 1 by the factor of x minus 4. So you go for the first term. How do you change x minus 4 to x cubed? We have to multiply it by x squared. So you get x cubed minus 4x squared. And then you subtract that from there. So these will cancel each other out. And then you got negative 5 minus negative 4, which gives you negative x squared. And then you bring down the next term, which is the minus 6x. So it'll be minus 6x. And then what you have is, how do you get negative x squared from x minus 4? We have to multiply it by negative x. So you get negative x squared and then plus 4x. And then take the difference over here. So then these are going to cancel each other out. So you got negative 6 minus 4, which gives you negative 10x. So then how do you get negative, and then bring down the 1 as well next. How do you get negative 10x from x minus 4? You have to multiply it by negative 10. So then you have, so that's plus 1, sorry. And then you got negative 10x and then plus 40. And then you're going to subtract this. And finally, your remainder is going to be negative 39. So this is your remainder that cannot be divided by a linear factor anymore. So your remaining is going to be x squared minus x minus 10. So that's the quadratic that's resulting from dividing that cubic out. And then your remainder being minus 39 over that linear factor. So that's your answer. Okay, next, part C. If P equals 3 plus 4i, and then Q equals 1 minus I, and then R is equal to negative 2 plus 3i. Find the complex number Z such that PZ plus Q equals R. So we're also going to let Z equal x plus IY, because we don't know the complex number of Z. So we want to satisfy the equation P times Z plus Q equals R. So P being 3 plus 4i, Z being x plus IY, Q being 1 minus I, and then R being negative 2 plus 3i. Okay, well, so here you can immediately choose to bring all of this to the other side. So then that gives you negative 3 plus 4i, and then we can, we're then left with, we can expand this part over here, gives us 3x plus 3iy plus 4ix plus 4i squared y. The I squared becomes negative 1, so we can just write that as minus 4y. And what we know is that the real part on the left side must equal to the real part on the right side. So the real part on the left side is the 3x and the minus 4y. And this must equal to the real part on the right side, which is negative 3. And then the imaginary parts must equal to each other. So that is the 3y plus the 4x, and that should equal to 4. So you can then form simultaneous equations to solve for x and y. So you're going to go to your calculator, simultaneous equation, two unknowns. The x term is 3, and then negative 4, and then negative 3. The next one, well, I mean, it's just the other way around, but make sure you put in 4 for the first term for x, and then 3, and then 4. And then you'll get x being equal to, x equals 0.28, and y equals 0.96. So your complex number for z is going to be, z is equal to 0.28 plus 0.96i. Yeah, that's my answer. Okay, next is going to be part D. Write an expression to represent the resulting complex number z over conjugate of z, where z equals x plus iy. Give your answer both in rectangular form and polar form. Okay, so you have z equals x plus iy. So the conjugate of z being x minus iy. So then z over its conjugate is going to be x plus iy over x minus iy. And with all imaginary numbers in the denominator, you need to rationalize it by multiplying by its conjugate. So this you need to multiply by x plus iy. So then the top just becomes x plus iy squared, and the bottom becomes x squared plus y squared. Expanding out the top, we get x squared plus 2ixy, and then you got plus I squared y squared, and we know I squared is just negative 1, so we're going to change this to negative y squared, and that's over x squared plus y squared. So in rectangular form, you're going to separate out into its real components and its imaginary components. Its real component is x squared minus y squared over x squared plus y squared, and the imaginary part is 2xy over x squared plus y squared times I. So that is the rectangular form. So then we can convert this into polar form. So to convert this into polar form, into z over z prime is equal to r cis theta. Remember that r is defined as the square root of the real part squared plus the imaginary part squared, and then theta being the inverse tangent of the imaginary part divided by the real part. So then we know that the real part of this expression is the x squared minus y squared over the x squared plus y squared. So that's going to be the square root of, square root of all this. This is the x squared minus y squared over x squared plus y squared, all of that squared, plus the imaginary part, which is the 2xy over x squared plus y squared over x squared plus y squared, all squared, and then cis, and then the angle is going to be the inverse tangent of the imaginary part. The imaginary part was the 2xy over the x squared plus y squared over the real part, which is the x squared minus y squared over the x squared plus y squared. So a few things cancel out here. So you'll notice that these will cancel each other out. So then your cis expression is just going to be the inverse tangent of 2xy over x squared minus y squared. But for this huge brackets here, notice how the denominators are both the same, right? And they're both influenced by the squareds here. So they're both going to be, the denominator is going to be x squared plus y squared all squared. So the top of it would look like x squared minus y squared squared plus 2xy squared over x squared plus y squared squared. And this square and the square root, they can cancel each other out. we can get rid of that. And then we can reduce the square root down a little bit. So let's continue this over the next page. So continued, where z over z prime, conjugate of z. So we had the square root of x squared minus y squared squared plus 2xy squared over x squared plus y squared squared. And we can simplify the cis expression to inverse tangent of 2xy over x squared minus y squared. So as we explained, we can get rid of this squared using the square root. So we have the square root of, well, we can expand out the brackets here. We get x to the power 4 minus 2x squared y squared plus y to the power 4 plus 4x squared y squared, square root all that, and that's all divided by x squared plus y squared, and again still times by that cis of inverse tangent of 2xy over x squared minus y squared. And then over here you'll notice that the top you can collect like terms, this term and that term, join to x power 4 plus 2x squared y squared plus y to the power 4 over x squared plus y squared. Noticing here that the inside of that square root is actually a perfect square, and that is the perfect square of x squared plus y squared squared over x squared plus y squared. Sorry, that's squared. So then you can use the square root to cancel out the squared over there. So all you're left with is x squared plus y squared over x squared plus y squared, which simplifies down to 1. So all of this actually cancels out to 1. These don't actually mean anything. They're all cancelled out to 1. So all we're left with is just the cis component that I've not bothered to write here. But the final answer is just going to be cis of 2xy over x squared minus y squared. That's it in polar form. That's what I would do there. Okay, the next question is for two complex numbers. So this is part E. Two complex numbers u equals a plus ib, and then v equals x plus iy. Show that this inequality exists. The modulus of u plus v is less than or equal to the modulus of u plus the modulus of v. Okay, so again, we just need to substitute all these in and then prove that it is true. So you're just trying to simplify this as far as possible, in my opinion. So the first part, a plus ib plus x plus, x plus iy, less than or equal to the modulus of a plus ib plus the modulus of x plus iy. Group the real parts on the left hand side as a plus x and the imaginary parts as b plus y. Keep that all the same. And then we can take the modulus on both sides. So this is going to be the square root of a plus x squared plus b plus y squared, all rooted, less than or equal to the square root of a squared plus b squared plus the square root of x squared plus y squared. Okay, and then we can simultaneously expand out the insides of this one, and then we want to square both sides to get rid of the square roots everywhere. And when we square the left side, it gets rid of the square root, and let's expand it out. So yeah, a squared, a squared plus 2ax plus x squared plus b squared plus 2by plus y squared less than or equal to a squared plus b squared plus 2 times, so this is expanding out a binomial, so a plus b squared gives you a squared plus 2ab plus b squared. Right, so I'm just going to simplify this as square root of a squared plus b squared multiplied the square root of x squared plus y squared, and then plus x squared plus y squared. So you'll notice here that the a squareds and a squared cancel, x squared and x squared cancel, b squared and b squared cancel, y squared and y squared cancel. So all we're left with is, on the left hand side, 2ax plus 2by less than or equal to, these are two square roots multiplying by each other, so you can multiply the inside components together. So this is 2 square root of a squared plus b squared times x squared plus y squared, and all of this is square rooted. Notice that you got a factor of 2 everywhere, so you can cancel out the 2 here. So all you're left with is ax plus by less than or equal to the square root of, let's expand out the inside of the brackets over there. So you get a squared x squared plus a squared y squared plus b squared x squared, and then plus b squared y squared. Reason we're doing that, because we then need to square both sides to get rid of that square root. So then squaring both sides, you have ax plus by squared less than or equal to all of this. So then expand out the left side brackets. You get a squared x squared plus 2ax by plus b squared y squared less than or equal to all of that. And you'll notice that in the square root, you got a squared x squared cancelling with the a squared x squared there, b squared y squared cancelling with the b squared with y squared over there. So you're left with 2ax by less than or equal to a squared y squared plus b squared x squared. You bring everything to the left side and you're left with a squared y squared minus 2ax by plus b squared x squared. This is also a perfect square, where you have ay minus bx all squared. So this inequality remains true because you have two cases. If ay equals bx, then this expression ay minus bx squared is going to equal 0, because ay minus bx, if they're equal to each other, it's going to cancel each other out, and then it's going to equal 0, and then 0 squared is 0. But if ay doesn't equal bx, then this expression ay minus bx is going to be the difference between two numbers, and regardless of whether or not these numbers are, if the result between the difference between them is negative or positive, it's always going to be greater than 0 because it's a squared number. The square of any number is always going to be positive, and so any combination of a, y, b, and x is going to satisfy this inequality, and so therefore it is always true. And so we have solved that this is true. Well, this is proof, I guess. Okay, and that's that question.